So I didn't run out the full, but essentially like
This one is the regular.
yeah, this is triangle. And then this is without like one and the other one. And because like when you take the taking the min cancels out this on one side.
Okay,
The
cool.
reciprocal is like
Okay.
this is less than one, and the reciprocal has to be
Yeah,
greater.
that is one.
And so that's why like it cancels on either side.
Okay.
But once
So
you
basically,
remove
it's,
it
as it's back, it should be like 50 because
So,
it's from
Yeah, so-
less than
So
20
here you're
minutes.
still taking
that's
min,
the
so when I was
difference.
computing it, it's
Okay,
still within
okay,
the reciprocal. If one was
Thanks.
equal, then the other one would be less than.
Yeah, this one, I don't remember how to write that. Okay.
When we started the very first semester on Friday, because she also had an assignment.
Yeah.
Oh, yeah, I was looking at the notes and it sounds like you were sampling one, and then the next one you sampled and you updated the previous one, and then when you sampled again, you would use the updated one. Which, so that's
Yeah, that's okay.
but why is that different? Like, why were we only sampling one thing here? This shows a detailed balance goal, but does that mean that if we sample multiple, then oh, so for this one, so for this problem, because it's a base net, we have to sample like for every single node. And then, but I thought we were given, no.
Alright. Welcome back to 7-4-18-6-18. Today we're going to be talking about a really fun topic, which is that of learning from partial observations. And we'll do that in the context of a framework called variation EM. Before we get there, we actually have a little bit more with mean field variational inference to wrap up. And then we'll kind of move into this new topic. So one good question that came up at the end of last lecture was, what on earth were you talking about with the reduction of map inference to variational inference? So afterwards, in office hours, I started sketching out a little example of what it was that I was talking about. Let's actually pull up the notes from that discussion, where let's see. So what we were thinking about in the context of variational inference here was how we could take map inference, kind of cast it as variational inference. Like this. And this example on the right-hand side is new. We didn't talk about it last time. And what I did is I said, okay, well, recall the map inference problem, right? It's just about finding some z hat that maximizes, p of z given x. So let's suppose we have this little example where we have two random variables, a and b, and they can each take values red and blue. So there's 4 distributions that I want you to think about. Okay? Those are Q1, Q2, Q3, and Q4. These are funny distributions because, okay, so a distribution over A and B has to give 4 probabilities, right? 1 for each of the possible configurations of A and B. But these 4 distributions are funny because I made it so that they that's odd. That would be problematic. Weird. OneNote has sort of stopped functioning on us here. see if we can get it back up again. Huh. Okay. I think we'll manage even though it's not fully functional here. Okay, so what we're thinking about is basically this setting where we have these 4 different distributions over A and B, and each one is a point mass distribution, meaning that it puts all of its probability mass on one of the configurations, one of those A-B configurations, and then it gives 0 probability to all of the other configurations. So I listed out the 4 different possible Q functions of this variety, and I didn't list out any other possible distributions, because I want to call those 4 distributions our Q family, our variational family. Okay, so suppose that the true distribution over A and B is the green column, where we have, 0.2, 0.4, 0.1, 0.3 as our probability distribution. If we solve this KL divergence problem, which is what variational inference solves, then what we're saying is, find me the Q distribution in our family of Qs that minimizes the KL divergence between Q and P. So the question is, which of these 4 minimizes KL divergence? Well, we could actually just measure it, right? It's just, in this case, you can exactly compute the KL divergence. So you could compute KL for each one of these, and what we would find is that the KL divergence is minimized with Q2. Why Q2?
One is at the max of 2.
Yeah, exactly. And the KL divergence is just going to look like the value of Q times the log of P over Q. So all these cases where Q is 0, those just don't even contribute to the sum. And only the term where we have Q equal to 1 actually do we contribute to the sum. And so, naturally, we want P to be at its highest for that term in the sum. Okay, so here we reduce map inference to variational inference. Okay, so this is illustrative. I'm not suggesting that you actually go out and implement map inference in this way, but rather that it's important to understand that what you're doing when you solve this map inference could be interpreted as a form of variational inference. So the whole point of this example is just sort of show the flexibility of the framework that we've built up. Okay, so any other questions just while we're sort of pausing here? Yeah.
So Q family can include all of the possible distributions that can be made. So variational inference doesn't put a limitation on the kind of distribution that can be made.
Exactly. So yeah, that's the sort of key property of the variational approximation is what does that Q family actually look like? And that's going to define everything about it.
So when you don't have like that finite state of Q's, when you're like learning what Q is that like learning the parameters of Q?
Yeah, exactly. So that's what we're really going to be doing in the rest of today's discussion of mean field is thinking about how do we actually learn the parameters of Q rather than sort of picking out a specific Q from a list. Okay. So anyway, I think this is a great sort of mental example to work through. So the usual reminders, and I guess for 618 students, just a note that we're going to be releasing your project proposal feedback, I think today, this afternoon, and then the submission for the midway poster is on Thursday. And here, it's sort of important for you to keep in mind, the whole point of this midway poster session is just for us to kind of give you actual feedback in an even more sort of interactive form than sort of what we'll be doing with just sort of writing you a few notes in response to your written proposal. So yeah, so we hope this is sort of fueling interesting discussion. I've never actually seen another class do this before, so it's a little bit of an experiment. But I think it'll be kind of a useful forcing mechanism for us to have conversations early about what your plans are. Okay, so to wrap up mean failure, so we spent a lot of time talking about variational inference. And what I want to wrap up with is, so we actually already did this algorithm summary, but we skipped over this discussion of the actual derivation of the coordinate ascent variational inference algorithm. And so today I actually want to look at why it is that coordinate ascent variational inference works as it does. And so let's pick up there. Okay. So the whole idea of coordinate ascent variational inference is that, and maybe we'll actually go ahead and just kind of grab the algorithm summary from last time so that we can go ahead and recollect what it is we were talking about here. Except that, Okay, well, nope. I guess we won't. Okay. So, so this is what we were saying about coordinate ascent variational inference. We said that the algorithm is going to proceed just iterating through each variable. So we said we have t variables. And while the elbow has not converged, we're going to make an update to that qt of zt, which is to set it proportional to x of an expectation of a log of the probability of zt given all the other variables. So the inner term, that log probability, should look really familiar. That's just the full conditional from Gibbs sampling. And what's different about this is that we have this expectation under the Q distribution where we've essentially made an expectation given by all of the variables except for Q. And so when we say that we want this Q to be proportional to something, we're saying, okay, well, you're actually going to have to normalize this. And so we'll look at a discrete case where you can just enumerate out all of the these quantities and then just sum them all up to normalize them. Okay. Okay, so why is it that we end up with that that update rule for coordinate ascent variational inference? So essentially, what this boils down to is it's essentially a function of two important properties. One is the chain rule of probability, and the other is the mean field approximation that we made in Q. And so the first thing that we're going to do here is, so just recall what we call the chain rule of probability. And apply it to the joint. To what we call P alpha. So what this looks like is we have this joint distribution, which is P of that vector z, and what we're going to do is we're going to actually, so rather than talking about z as some abstract vector or over some unknown number of variables, we're actually going to subscript z to show the variables that are involved in this vector. So z subscript 1 colon t means z1, z2, z3, all the way up to z capital T. So the joint distribution is then, say, z1 colon t and x1 colon, let's say m, where we have m input variables. And so if we want to apply the chain rule of probability here, what we're going to do is we're going to say, well, first, we have this joint probability over all of the x's. And so actually, let me just sort of the chain rule here, just in case it's been a little while. So P of A, B, and C is equal to P of A times P of, say, B given A, times P of C given B and A. And we could write that out in any order for those three variables. So here we're going to do the same thing. And so the first sort of actually group of variables that we're going to put together are all the x's. And then all of the other terms we're going to collect into this product, which is little t up to capital T, of the probability of zt given z from 1 up to t minus 1 and all the x's. So essentially, we've just said that zt depends on all of the z's up to and including t. And notice that this is not for a specific kind of factor graph. I mean, this could be any sort of arbitrarily interesting factor graph that we might have over a collection of variables here. And there might have cycles in the factor graph, and there might be lots of interesting dependencies between the x's and the z's. So we're not saying anything specific about the actual form of the factor graph that we're working with here. So the next thing that we want to do is to actually decompose the entropy of the variational distribution. So here, what we have is the entropy of q theta. And so the q distribution that we're working with, we're going to say that the elbow consists of two terms. One is expectation under q of log p of x and z, and the other is expectation under q of log q. So that's the one that we want to work with. So the expectation under q theta of, oh, and I guess above I actually dropped the parameters alpha, just because we'll kind of bring them back in as we need them. So here, we could say p alpha all through here, just so that we don't lose track of the fact that this is parameterized by alpha. Okay, so this is the entropy, which is going to be q theta of z 1 up to t. And so this entropy, because of the actual form of the mean field approximation itself. So let's first say, so this expectation is going to be a sum over z1, z2, up to z capital T, right? And then the term, let me actually make this in sort of two steps here. So the first step here we should write is just writing the expectation as a sum. So summing over all z's, 1 up to t, we have q theta of z1 to t log q theta of z1 to t. So we can rewrite that sum by breaking out into sums over each of the individual variables. And then we can replace the q thetas with the mean field approximation. So that would be a product from t equals 1 up to capital T of qt zt, and that's with parameters theta. So that's our first term here. And then we have this log of the mean field approximation, and that we can actually push the log through this product, right? It's really just the log of that product, but we can push it through that product to get back a sum. So we'd have a log of qt zt theta. And so then the last detail is we can actually do some tricky rearranging here, but it's not that tricky, or it shouldn't feel that tricky, because you've done lots of similar things with variable elimination. And this notion of kind of being able to shift these different summations and products around by commutativity is sort of one of the key properties of getting things to work in this class. And the punchline is that after we've done so, we get back a sum over just t equals 1 up to capital T of a bunch of mini expectations, which are just summations over that particular variable, where we have q zt theta times log q t zt theta. And we could rewrite this as an expectation under t different distributions, right? Each one is now under the distribution qt of log qt. So essentially what you can think of this as accomplishing is this is now the entropy for one variable. Or really it's the marginal entropy. And so here, we can now take sort of these two pieces together and decompose the actual elbow. Okay. So what does that look like? Well, we're gonna, and I guess I should be careful here. So I have these summations over z, and so all of these and we should note that these would actually be integrals if z are continuous. But the actual sort of algebra works out to be the same. Okay, so now what we want to do here is say that our objective function, the elbow, can also decompose. Okay, and the key property to how we're going to go about that, Oh yeah.
Shouldn't the entropy is like log of 1 by Q?
Log of
1 by Q. Or just to make it the same?
So we, I think this is the second term in the elbow, so let's write down the elbow, just so that we actually remember what the elbow is. So elbow of Q theta is an expectation under Q theta of, it should be first the log of x and z minus the expectation of log Q theta of z. So I just took this minus and pulled it out and then wrote that in terms of the second term without the minus. So we should actually, if we're talking about, let's just put quotes around entropy here, and then say, you know, if we really want to talk about entropy, we should fold that minus back in. Okay, great catch. So, without the minus. So, okay, so now we want to decompose the elbow, and the trick is that we're only going to think about the elbow as a function of one of the Q terms. Okay, so why are we going to do this? Well, so the key, let's just jot that down. So the key idea here is treat the elbow as a function of qt, zt theta. Really, this is the whole distribution. So it's not for like a specific zt. It's for all possible zt's, right? So treat it as a function of this little variable specific distribution, keeping the others fixed. So why would we want to even do that? Any thoughts? Why would we even want to treat the elbow as a function of just one of the qt terms? Where are we actually going with this? Yeah.
Because we're moving one coordinate at a time.
Exactly. We're developing a coordinate ascent algorithm. And really it's not actually coordinate ascent, it's actually block coordinate ascent. Because what we're doing is we're taking the whole block of values here for this mini distribution, and we're going to update this distribution, leaving all of the other ones fixed. And so, if you were to choose the value of this that maximizes the elbow, keeping the others fixed, then the way that you could do that is just how you always kind of find a maximum, which is take the derivative, set to 0, and solve. So that's where we're going.
Does this mean that alpha is fixed throughout the entire elbow algorithm?
Yes. So here, alpha is always fixed. And so, I mean, what we're going to do later today, depending on how far we get through this stuff, is completely rethink that and say, okay, now we're going to also update alpha. But we're not there yet. So right now, alpha is fixed. Okay. Because we're doing block coordinate ascent. Okay, so so now let's write elbow, and we can write it as elbow of qt, or rather of say qt given theta. And so we're going to write that by kind of combining the two pieces that we just put together here, which is to say we're going to have and maybe at this point we should actually switch to, maybe we should actually switch to integrals here, just so that it's really clear where we're actually, and I think summations are fine. I'll just kind of call out explicitly where we need to switch to integrals. So this is a sum over variable zt of qt, zt, parameterized by theta, times an expectation, and this is the interesting part. We want this to be an expectation under just the distribution of everything except for the, oh, actually, let me go back a step here. So we'll get to that in just a minute. So first we want to write it in terms of the decomposition of the chain rule of probability. So what we have then is an expectation where we now take the expectation under q theta of the log of p of zt given, or sorry, not zt, but yeah, that's right, z of everything except for t, so that's z of not t, and x, minus an expectation under qt of the log of qt, zt. Oops, and this is also under qt. Plus a constant. Okay. So what I'm claiming here is that this elbow of q theta is actually equal to what I just wrote, right? So this normal elbow is equal to this plus a constant if we're thinking of this as a function of just qt. Because what we're essentially doing is we're saying, well, we have this expectation over the joint of z and x. Okay? And there's all these terms. There's p of x, there's p of each of the individual terms in that product. And we get this by saying, by essentially applying the chain rule with zt last. In the order. Okay. So whatever zt is, apply the chain rule to our joint, making sure that it's the last in that product, the last term in that product. And then here, we have an expectation over all of the different zt's, or sorry, a sum over expectations for all of the different zt's. But let's just push all of the ones that don't involve qt into this constant. Okay? And all of the terms from the chain rule that don't appear to, that aren't directly a function of zt into this constant as well. So that's all of them except for the last one, which we kept. So maybe we should, just to be really obnoxiously clear here. So where our constant is equal to an expectation under Q theta, or an expectation sort of under everything except for t. So we could write that as like Q not t of P of x, 1 to t, and the product from t equals 1 up to capital T minus 1. Or rather, let me write it the other way. Oh, sure. Okay. So here, so this is a product from all, say, t prime not equal to t of P of z t prime given z 1 up to t prime and x. Okay. So we've discarded all of those terms in this product, except for the last one. So here in a second. And then we've also discarded all of the terms in the sum over t primes not equal to t, where we have expectations under qt prime of log qt prime zt prime theta. So what we're doing here is basically saying we only care about some of the terms that are actually showing up, right? We only care about the terms involved that actually touch ZT. And all of these other ones, we're just pushing into that constant. Okay, so now what that means is we can write the write this thing. So we're gonna sort of rewritten without the expectations. This would be a sum over zt of qt zt, and here I'm going to leave all of the parameters out, of p of zt given z not t and x. Okay. So this is one expectation, and then the other expectation is a sum over zt of qt zt of log q zt. So now we've really gotten rid of most of the terms in this thing. And so all we have is a sum over the different values it could take on. It's really just this expectation under qzt of the full conditional for zt minus the entropy of that distribution. Okay. All right. So then the last step here is that we're going to take the derivative with respect to qt-zt. Oh, yep, we did miss a log here. Wait, there, thanks. So let's call this, say, L sub t. Okay, these two terms. But I guess actually we can even keep the constant around, because when we take the derivative, this constant is going to go away. Okay, so elbow written in terms of t is going to be LT. So what does that look like? It's going to be the derivative of LT with respect to QT ZT is just going to be an expectation under make sure I have this right. Oh no, I actually messed this up. So let me make sure I figure out where I messed this up. So let's see. Okay. So I was actually wrong about how easily we can get rid of this term. Okay, so in fact, the first expectation up here, so we have these two expectations when we rewrote the elbow. And the first one is not an expectation under QT, it's actually an expectation under the full Q distribution. Because otherwise, we don't have any notion of where these ZT terms actually came from. Okay. So that expectation, it's not under QT, and I think I actually wrote this and then I looked at it and I corrected myself. So I wrote it correctly the first time. It was actually an expectation under Q theta. Because we need the distribution over both ZT and Z naught T. Okay? It's not like Gibbs sampling where we have a specific assignment to the other variables. We actually need a distribution over the other variables. Okay, so my mistake then was in this rewriting of the whole thing. So now we're going to make some space and actually get this log back in here as it should have been from the beginning. And as well, so here's the log where it should have been. And we also need, what we're really doing here is just factoring out one of the terms in the expectation. So this is still an expectation under Q naught T of this log. So this is sort of my key mistake, right? That this whole thing is an expectation under Q naught T. So that's really important here. Right, and the way that I did that is that an expectation under Q theta is just a product of Q1, Q2, Q3, Q4. So it's trivial to pull one of those terms out of the expectation and then get a sum. Okay, so now when we take the derivative, what we get back is essentially something really simple, right? Now, if you look at this, these two sums are just, so in the first case, it's just sort of a linear function of QTZT. Right, so if I take the derivative with respect to QTZT, then all we have is the expectation under Q naught T of that log of the probability of ZT given Z naught T and X. Minus just one of the terms in that other summation, which is going to be log of QTZT. All right, so the key observation here is that I'm taking this derivative with respect to a specific value ZT. Right? So here, I remember this was actually, if you remember when we were doing these factor derivatives, when we were first looking at how do you learn a CRF. This was actually sort of one of our major sticking points, was we were talking about taking partial derivatives with respect to factors. Okay? And what we were doing was taking partial derivatives with respect to one entry in a factor. Here we're doing the same thing. Qt is a distribution over the variable zt. So it's like a vector. And we're taking the derivative with respect to one entry in that vector. So if this is, say, Qt, it could take on maybe 4 different values, like red, blue, green, violet. Okay. And there's going to be different values for those, right? 0.4, 0.2, 0.2, 3, 0.1, 2. Oh, no, 1. And we're taking the derivative with respect to, say, the green cell. So in the first sum, only one of those is a function of the green cell, and the other terms in the sum are constant with respect to that green cell. In the second term, likewise, only one of them is a function of the green cell. So that's why those summations drop away. Okay, so now the next step is set to 0 and solve. Okay, so here let's set this thing to 0. Okay, and now solve for QTZT. And what do we get back? We get back that QTZT should be proportional to exp of an expectation under Q except for T of the log of the probability of ZT given all of the other variables Z not T and X. And that is, so this, oh, sorry, and there's sort of two important, there's an important detail here. So the important detail is that if you're actually solving this, you need Lagrange multipliers. To ensure that Qt sums to 1. Okay. So how many of you have, figured out the maximum likelihood estimate for a multinomial distribution before in some probability class along the way? Have you all done that? Okay, some of you, maybe not all of you. So if you're asked in a probability homework to get the maximum likelihood estimate for a multinomial distribution, you can't just maximize the likelihood of the data with any old parameters. The parameters have to sum to 1. And so that's a constraint on the parameters. And so when you're, setting equal to 0 and solving, you actually have to fold that constraint into the objective via Lagrange multipliers, and then you solve it. And, or then you take the derivative with respect to that Lagrange and solve. So, so this is the punchline in that, our punchline here is that this is the value of QTZT that maximizes the elbow. So, so now going back to the coordinate ascent variational inference, what are we doing? At each time step, all we're doing is we're saying keep all of the Q's fixed, and then update QT to be the one that maximizes the elbow. That's this update rule. And then move on to the next variable and so on.
Can you go over what's fixed and what's like variable? Because I thought that you said we were fixing just like the QT and then the Q naught T as a distribution because we don't know that variables. The other variables. The P of CT given Z naught T.
Yeah, so let's sort of reiterate the CAVI algorithm here, just so that we can see it. So it's while elbow of Q has not converged, we're going to say iterate through T equals 1 to capital T, so for each variable. We're going to keep the distributions Q1, Q2, up to QT minus 1, and then QT plus 1 up to QT fixed. Okay. So those are distributions, right? They're not, it's unlike Gibbs sampling because we actually have these tiny little distributions over the variables. And what we're saying is then update QT to be proportional to this rule. Okay, so let's actually instantiate this for a particular case. Oh yeah, question.
So can you get go back to the page? So I mean, like, why is it like proportional to that? Shouldn't it be like exactly equal to that if you're just solving for set t at a particular time? Like if it is equated to 0, shouldn't it be like qt dt exactly equal to exponential?
Oh, you mean if we just solve for log QT?
Yeah.
Oh,
Since we are solving for a single set t at this moment.
yes, yeah. So if we don't have the sum to 1 constraint, then you just solve that for log QT, then you get QT equal to this. Okay, but we do have a sum to 1 constraint that says the total sum of all of these things needs to add up to 1.
So we are kind of solving for all the equations that should come.
Exactly. And so you could imagine that exponentiating some expectation like this might actually give you back a bunch of things that do not sum up to 1. Like maybe one of them is 7, and one of them is 4, and one of them is 9. Okay, so the probabilities for QT are proportional to 7, 4, and 9, but you actually need to renormalize them to get back the sum to 1 constraint. Yeah, so that's what you're seeing there is actually like the effect of the Lagrange multiplier is just that it changes that from equality to proportionality. Yeah. Okay, so now let's do a sort of example of this, which would be multinomial full conditionals. Okay, so this is a common case where we have zt is discrete for all t, and finite valued, meaning it can only here's our example. So zt is discrete and it comes from a finite number of values. Okay, so like red, green, blue, violet. So what we have then is suppose that the full conditional p of zt given z not t and x is defined to be equal to some pi of or some, say, pi of so let me be careful here. So this would be pi of ct given. So this is sort of funny. What I'm saying is, suppose that the full conditional, you can actually write out as a little table. Right, like this is some table. And it just has entries for the different z values. Okay. Then what we have is that this like q star of zt, that update rule, is that this should be proportional to exp of an expectation over the log of this distribution. Under pi. So this, I mean, you could just compute with a for loop, right? It's just a sum over the actual full conditional. So once you can actually like write the full conditional as a little table, evaluating this is trivial. Okay, so if the full conditional is not just a multinomial, then we get into exponential family distributions. And we'll just say these are not covered today. So exponential family, this includes lots of sort of familiar distributions. So, things like Gaussians and exponential distributions and lots of other ones. So if you have continuous distributions that involve sort of familiar distributions, then you also get simple update rules. Okay, so now I think one of the last and maybe most useful things that we can do here is that So I want to actually think about a two-variable factor graph. Okay. So we're going to say we have one red variable, call it A, and one blue variable, call it B, and we'll say they're connected up by a single factor. So we could further say that this true distribution, so this is our P of alpha of A and B. And our true distribution is going to look like a little grid over the possible values that A and B could take on. And let's say there's 9 different values that A can take on, and something like 1, 2, 3, 4, 5, 6, 7, 8 different values that B can take on. So this is A, and this is B. And that we're going to represent the probability distribution by shading in certain regions that are high probability. And so maybe the distribution that that actually holds between these two variables is something like this. Where that's sort of the high probability mass region. And everything else is kind of low probability mass. Okay, so what we could do then is we could and actually let's maybe put a little bit more probability mass down in this corner. Okay, so that means that we could actually take a marginal probability. So this would be the marginal P alpha of B. Right down here, this black thing is P alpha of A and B, the joint. And we could also look at a marginal probability P alpha of A. And what we would find in these distributions is that here the marginal probability for B puts most of the probability mass kind of around here, and then a little bit off in this corner from these sort of two most dense regions. And then similarly, if we looked at the marginal probability of A, it might kind of shade in most of these parts and this part. The sort of middle here and the bottom down here. So if we were to run something like a mean field approximation here, then we might have an A and a B that were completely disconnected. So this mean field approximation is Q theta of A, or rather, let's just write the whole thing out. So the mean field approximation is Q theta of AB equals Q theta of A, Q theta of B. And essentially what mean field is doing is it's saying, well, we're actually able to reconstruct a joint distribution that approximates the true joint distribution. And the way that we do that is by taking Q theta of B and q theta of A and multiplying them together to get an outer product. So maybe here, most of the probability mass in q theta of B is here, and most of the probability mass for q theta of A is here. And when we multiply them together, we kind of get some probability mass that puts most of its weight in the corner there. But maybe it actually misses these sort of diagonal parts of the actual distribution. So lastly, the sort of interesting bit about this is that the CAVI algorithm here is just going to go back and forth between updating q theta of A and then q theta of B, q theta of A, q theta of B, right? So maybe we start out with, say, so we initialize q theta of A, say to be some little distribution, say it's just 2 values, and it works out to just be, you know, the uniform distribution, 0.5, 0.5, and q theta of B, also uniform, 0.5, 0.5, right? So here, so now assume that A is just in 1, 2, and B is also just from 1, 2, right? So now I've just sort of shrunk these grids. So our joint distribution now looks like this. So CAVI is going to initialize q theta of A and q theta of B. And then it's going to update q theta of A as some function of this q theta of B. And then it's going to update q theta of, and that'll give us back some new values for q theta of A. Maybe it's that this is 0.7 and this is 0.3. So then we update q theta of B as some function of these. And that gives us back a new distribution, which is maybe something like 0.6, 0.4. And we just repeat this back and forth, right? Now we go back to A. Q theta of A gets updated as some function of these values. And maybe now it's concentrating 0.9, 0.1. And then finally q theta of B updates to some function of these, which is maybe 0.7, 0.3. And we just run this until convergence. So, if you want to think about what a Gibbs sampler is actually doing here, a Gibbs sampler is doing something a little bit different. A Gibbs sampler is saying, suppose what we did was we just kept track of a fixed point estimate, ZA, and a fixed, let's make that blue, a fixed point estimate, ZB. And then we had some joint estimate of the whole vector that was the vector z consisting of ZA and ZB. So in this case, what the Gibbs sampler is doing is it's saying, okay, well, at any given moment, we're assigning, it's like we have a point mass distribution that puts all the probability mass on some specific assignment to these A and B variables, right? And that corresponds to, I guess this is position 4 here, so corresponds to some specific entry in the joint assignment. So the Gibbs sampler is sort of taking a step and updating the value of ZB. Maybe it moves to here. Okay. So that would be like moving the joint to this new place. So if we resampled the value of ZB, that's effectively like moving the value of the point estimate. And now, if we then resampled the value of ZA to this one, that's like resampling here to move down 2. And so the Gibbs sampler is just kind of walking around in the space, essentially using these kind of point estimates and giving us back a sample at every iteration. Whereas mean field is actually updating these like mini distributions over the actual whole variable itself. So, let me leave you with one parting thought here, which is, why do we go to all this trouble? Let's think back to what we would get if we were doing exact inference on a grid CRF. So this is useful if you want to do something like pose estimation. It's useful if you want to do, really any CRF in Vision. Like say you wanted to do image segmentation or semantic segmentation like you guys were doing. So we probably have lots of unary terms, lots of pairwise terms, and you might have a grid conditional random field like this one, maybe backed by a CNN. And so if we want to do image segmentation, then let's suppose further that all we're trying to do is just divide into foreground and background. Okay? So each of these variables takes one of 2 values, either foreground or background, and each is a little table with 2 squared entries, each of these factors, right? Because it's going to have an opinion about the foreground, background values of 2 variables. So now, suppose we said, this mean field variational inference seems like a lot of work. Let's just do variable elimination, right? That was easy, deterministic, it gets us exact marginals. Okay, so you eliminate the first variable. It's actually really easy, right? Eliminating one variable here. And then you eliminate the second variable, and then the third, and the fourth, and the fifth. But now this new factor, it actually has 2 to the 5th entries, because it's now connected to each of these variables in the grid. Okay. And as you continue along, for an m by m grid, just after elimination of that first row, this factor has 2 to the m entries. So if your image is 100 pixels by 100 pixels, that factor has 2 to the 100 entries. Okay. So this is why we don't do variable elimination on a problem like this. Why we turn to approximate inference for methods like these. Okay. And so I'll start next time. I have a whole lecture here on variational EM that we'll pick up with. And I'll start next time by thinking about the case of a ridiculous fully connected CRF, where we don't just have pairwise factors. We have a factor between, or sorry, we don't just have like a grid of pairwise factors between adjacent pixels. We actually have a factor between all possible pairs of pixels. Pick any pair of pixels in the image, add a factor between them. So we'll pick up next time thinking about how we can actually work with this fully connected CRF in a variational inference framework. And we'll look at a couple other examples of just sort of the power of this method. And then finally, we'll get to dealing with sort of partially observed models. Okay, so I promised you that today. We didn't get through it, but we'll pick up there next time. Okay, see you then.
Oh, sorry. Mine's like a question.
Sure.
It was